Lactea is a multi-resolution, spectral-preserving binary tree data structure designed for spectral exploration and visualization. Each tree node contains two components, a list of stars and the spectra of its subtree. Stars are rasterized as points, while nodes at the graph cut are rendered as patches with uniformly distributed energy. On the left, we see the spectra of the selected region plotted. The spectra of stars and patches are accumulated in a 3D buffer, where the depth axis represents the spectrum. This data is processed to generate an RGB color representation. As the user explores the scene, the tree is dynamically traversed, and rendering cues are updated. Here, we zoom into the lower left region of the data to observe the Large Magellanic Cloud, one of the closest galaxies to our own. Next, we switch the rendering scheme to one based on intensity, using the color map displayed on the left. The highlighted region has a high intensity, which is mapped to yellow. In comparison, the purple region is 2 orders of magnitude dimmer than the previously highlighted area. Additionally, we can compute an RGB value by convolving the spectra with the CIE sensitivity functions. Blue regions correspond to spectra skewed towards the shorter wavelengths, blue, while redder regions indicate spectra shifted towards longer wavelengths, red. Now, let's explore some astronomy-inspired use cases of our system. Looking at the CIE view, we observe that clouds obscure certain areas of the scene, especially near the galaxy's center. These gas clouds scatter and absorb light, reducing intensity, particularly for shorter blue wavelengths, resulting in a reddening effect. This phenomenon is known as interstellar extinction. In our system, this effect is most apparent in the redder areas of the galaxy's center, compared to the fainter reds and blues in less obscured regions. Here, we apply an extinction correction. The image is brighter overall. Some regions, such as this one, are relatively unaffected by the correction, while others, like this area, show significant changes. The difference is especially noticeable in the intensity map when focusing on the central regions. The intensity map visualizes the total energy of the spectra. It's often useful to isolate specific parts of the spectrum for analysis. For example, isolating hydrogen alpha emission lines is achieved using narrowband filtering. However, narrowband filtering alone cannot distinguish whether the light comes from an emission line, a continuum spectrum, or even an absorption line. For instance, this region exhibits hydrogen alpha absorption yet still appears in the visualization. To detect emission lines, we can subtract the underlying continuum spectrum, which we estimate by smoothing the spectra using a Gaussian kernel, then apply narrowband filtering. After subtraction, the region with hydrogen alpha absorption disappears, revealing clearer distinctions. In contrast, this region shows interesting patterns after continuum subtraction, highlighting features that were indistinguishable in the original view.